So this is the last section of today, and we're going to have first presentation by Patrick Charbonneau from Duke University, cracking the glass problem, please.
Glass problems.
Problems.
Yeah, it's plural. It's actually part of the story. But before I dive in, I'd like to talk a bit about my own first encounter with Giorgio. Actually, the first words that Giorgio addressed to me were very good. Quite literally, they were very good. And this was a summer in 2011. I was working with Francesco in Paris, a sort of mini sabbatical. And this was the first email exchange that Giorgio sent me. So it was a very auspicious start because about a month later, we had submitted a PRL based on that work, or what was to become a PRL, and only 2 more months later, it was published. So this was I thought a great start for collaboration for someone with whom I'd never actually exchanged a word in person. And it's a few years later when I got to remediate this lacuna. I spent summer 2014 around the Mediterranean Sea, in Rome first, then in Cargèse and in Capri. And that's actually when we started planning an application to the Simons Foundation for cracking the glass problem. And I got to know Giorgio a bit more, spending a bit more time, and shortly after that, I became one of his friends. I mean, in that very narrow sense of friending someone, it's far from being a select club, right? This is just the subscribers to his feed. He has more than 2,000 now, I think, Giorgio friends. But nonetheless, this is very flattering for someone who's never actually studied or worked in Rome. And then shortly after becoming his friend, he started wishing me a happy birthday, right? At least in 2015 and 2016. 2017 he missed, but that's okay. 2018 is upcoming, just so you know. And happy birthday, Giorgio. Okay, bonne fête, I should say. The work I'm going to be presenting today is work that's been extremely collaborative and comes from a number of people. I mean, the people I put in bold here were the postdocs at Duke, who were or are at Duke, who's worked most closely with me, but it's not really a fair representation because all the names on that slide were essential to making the work happen, and including the fine older people there that are actually the members of the collaboration plus Mathieu, who's I think missing right now. And so what I thought, even though some of you are probably already familiar with some of the content, not all of you are actually structural glass scientists. So I thought I'd review or revise some of the notions, and in particular try to characterize a bit the title I started with, suggesting that there could be multiple glass problems. And because the glass problem is really in the eye of who's looking at the problem. If you're a material scientist, in particular, when you think about glasses, and the most important glass problem is the following, right? So you have a recipe for preparing glasses. You have a high temperature liquid, and then you can be monitoring, let's say, its specific volume or its specific enthalpy, and you cool it, and at some point that liquid should crystallize, right? This is a first order phase transition, thermodynamically driven. But what you want to make sure, and if you're a glass material scientist, is to make sure this spontaneous transition does not happen on any relevant time scale for your experiments, right? So you're trying to design your mixture such that you can actually supercool it, and then you design quench protocols and compositions that will allow you to obtain a glass, right? And in the eyes of a material scientist, the glass problem is really one of preparation in that sense. If you're a chemical physicist or maybe a statistical mechanics person, you consider the glass problem maybe more in that language, right? So presuming you have a material scientist friends who's managed to get you a glass sample, you don't have friends, or you don't know, sorry. So then what you'd find is that when you cool it, your liquid, your supercooled liquid, becomes really viscous really quickly. Right? It's quite remarkable for something that has no obvious structural changes. Right? If you take water through 0 Celsius, it does become much more viscous quite discontinuously, but so does its structure. Right? And if you do that for a glass, it's not I mean, this change in structure, if it happens, is not obvious to the naked eye. And on top of this, right, there's a number of, so if you look at, say, the log of viscosity versus 1 over temperature, there's a different classes of universality or different ranges of observational parameters you can see. So there are glasses that seem to slow down Arrhenius-like, as you'd expect for something that has a lower temperature to go over some barriers. But there are some glasses also that are fragile, meaning that they're, as you cool them down, there's a super Arrhenius growth of the viscosity. So not only do you not know where the barriers come from to begin with, but those barriers actually increase as you cool down your system, right? So it's a puzzle. If you're a low temperature physicist, you think of the glass problem as a different way. Yeah? And so you have material scientist friends who prepared composition, then you have chemical physicists who've cooled it and made a glass. Well, then you look at this glass and you say, well, this is a very interesting solid state problem now. I can just bring it to low temperatures and look at its excitations and look at its its transport properties. And what you find is that if you compare what you observe with what you see in your favorite solid state textbook, there's a mismatch. Right? There's a classical nomenclature for this mismatch. It's called anomalous. Right? Whenever you see something that doesn't match, you just call it anomalous. So you have anomalous density of state, you have anomalous transport, and in the 90s, almost 20 years ago now, there was a proposal to try to unify what's seen in those low temperature glasses with what's seen in zero temperature systems that are granular systems. Right? So these are examples of experiments that the late Bob Berenger was doing and is pretty famous for. What you're seeing are photoelastic disks, right? You can barely see them. They're about this size here. Photoelastic disks in which the system allows you to visualize the force network throughout the system. So you put these elastic disks under stress and you see those very strong heterogeneity in how force is transmitted through the system. Right? It's called jamming. This is when you have actually particles physically in contact. And the proposal from Liu and Nagel was that maybe there's some universality, there's some connection that relates what you see, these anomalous properties of low temperature glasses with those of, that you can see in jammed sand or jammed disks if you're trying to do this under control. Right? And these three problems, and a few more, right? If you want to be generous, I just don't do rheology. But if you want to be generous, there's a sort of a slew of problems that surrounds the glasses. And there was an article from the New York Times from 10 years ago that describes this. This is an anomalous problem, and it's a very famous problem, as I'm sure you know. And this is a quote from Dave Waits, who studied experimentally those model glasses at the time, and he's quoted as saying there are more theories of the glass transition than there are theorists who propose them. It's a slight to the theorists themselves. And this is a very interesting comment on the face value, right? It's obviously an exaggeration, but unfortunately not by much at that time, at least. But what it did to me is that it reminded me of another similar reference that's in Thomas Kuhn's book about the structure of our scientific revolutions, right? A philosopher of science from the 60s. And he's describing in his book the state of late 18th century chemistry, and actually oxidation chemistry, trying to understand the oxidation of metals. And there were phlogiston, so how the gases were interacting with metals. And it says, there are almost as many versions of the phlogiston theory as there were pneumatic chemists. That proliferation of versions of a theory is a very usual symptom of crisis. Right. So this is actually the theme of the structure of scientific evolution of Kuhn, right? He actually identifies all those critical moments and how these get resolved and science advances. That was his thesis. And Kuhn is quite generous actually in his essay, because he not only identifies those moments, he also tells you how they get resolved. He says that the answer is simple. All you need is a paradigm shift. Okay. Easier said than done. I'm sure the glass scientists for the 30 years before would have loved to find the paradigm shift and move on. And what I've argued is that this paradigm shift took place over the last from roughly from 2005 to 2016. It grew up in parts, and I say this actually, this little C here is my name, but I have a very, very minor part to play in it. So this is really meant as an honest perspective on how I think about this. And the paradigm shift was to solve the hard sphere phase diagram in the limit of infinite dimension, solve in a quasi-theorem way. It's not quite a theorem, but of that same flavor. Right, this is the same picture that Pier Francesco showed. Actually, the two people who led the early efforts were Giorgio and Francesco, and then the team expanded with Jorge, and then with Pier Francesco, and then with Corrado Renone, and then Hajime Yoshino. Right, so different parts of this phase diagram emerged. First, the equilibrium liquid here, which was actually understood separately in the high dimensional limit. Then the dynamical transition that was mentioned a number of times in Mathieu's talk, and the jamming line here that emerged. So I should say this is a 1 over pressure versus the packing fraction. So if you have something that's jammed, you actually have a mechanical contacts between particles, and that corresponds to an infinite pressure. So this is the jamming line, and it's really. It's a really beautiful and compelling picture. It actually sort of realizes the proposal of Kirkpatrick thermal ion Woolness for the random first order transition theory. The Kauzmann transition, which we'll come back later, on this scale appears infinitely far away, but is there as well. And it all brings this together. And this was a very exciting proposal, and because it allowed us, well, in part it allowed us to test a number of those predictions quite quickly. Yes? Who did I forget?
Could you explain what is the Gardner transition?
I will get there, I promise. So, and if you look at what was available at the time, which is not that far ago, from 2011 to 2016, right? Most of the simulations that you could do were actually in this regime. And if you could do jamming simulations, they were there. And if you believe, enlightened by Mathieu's comments, right? We think that maybe all experiments are in this regime as well, in one form or another, right? So we're not quite very far along this line. So there's really a lot of productive work that came out of this, working with Giorgio, and actually I should say the interface with Mathieu, which is another series of papers. These were all sort of exchanges back and forth, trying to pierce the understanding of the jamming line, were very productive. And this is what came out of this. But if you notice, right, this is a very unsatisfactory sampling of that prediction. Right? Everything happens roughly near the threshold line, right, close to dynamical transition. The predictions are being made for an entire slew of densities before this, but this was not acceptable. And on top of this, these regions are really not ideal if you want to be testing theories. There's a number of problems. If you want to be testing, I should say, mean field theory, because if you look at the finite dimensional simulations you can do, or finite dimensional experiments, there's a number of problems you encounter that pollute those predictions. Right? The first one is sort of obvious. These prediction does not make this theory doesn't make any precise statement about crystallization. The crystal is essentially absent from the infinite dimensional limit. So you have to worry about crystal nucleation. This is not so hard, it turns out, because this is a problem material scientists have been looking at for a long time. So we know how to create something that doesn't crystallize so easily. One of the other approaches we used in those early works was to increase the dimension of space. And if you increase the dimension of space, it also severely suppresses nucleation. So it sort of gets rid of this particular problem. This is the Franz-Parisi potential, as it's known. This is V of Q usually, but I like to think of it as a free energy, so I write F of Q versus the overlap. This is the same plot that Pier Francesco was showing again. So what this dynamical transition corresponds to, at least in the standard dynamics, is this flattening of this potential curve here, and then the emergence of a metastable minimum. And in infinite dimension, this metastable minimum is metastable for an infinite amount of time, so you don't really care whether it's metastable or not, to some degree. But if you're in finite dimension, there can be a path escape it. These are activated events. These are the ones that can interfere. And this has been appreciated for quite some time. And the traditional solution to look at this particular problem has been to try to patch a theory, right? So you have a mean field theory that's exact, or that at that time we didn't have an exact theory, but there were some understanding of what was happening, and then you try to patch this description with a nucleation theory on top of it, right? That's sort of a bit ad hoc and physically inspired nonetheless. Or another approach was to look in the crossover area, right? Try to go in a regime where nucleation has not yet happened, so you have a tiny window of time where this is not kicked in. Now there's another possible solution would be to increase dimension as we did originally, or if we could only go really, really far from phi d, then that drive to nucleate would be very, very small, right? The nucleation time would be really, really long, so that would also get us out of problem. There's another problem that happens, right? We are pretty familiar with this kind of free energy curve. We know that without disorder, the upper critical dimension of this is 4, and we're pretty familiar with the tools of how to fix this. But if you look at this sort of spinodal with disorder, the upper critical dimension is actually 8. So if you're doing simulations or experiments in 3D or in 2D, you're quite far. You're quite far from that regime, let alone, so there's activated events on top of this that are polluting it, but whatever is remnant of criticality is not even sure what it would actually represent. The traditional solutions, and actually what motivates Dave Waits in his snarky comment, is that there are sort of 2 families of solutions at the time. The first one was to wave your hands and say, well, that probably doesn't matter. And another family of solution was to say, well, this is all junk. Just throw it all away and look at it from a completely different point of view, right? Because we're so far below the upper critical dimension, how can this be of any relevance? Right? Now, what we were inspired with at the time of the reason, on those early papers, that we were able to sort of look more deeply into this criticality issue by increasing the dimension of space, right? If you do simulations in higher dimensions, you can sort of make the hand waving and the negativity sort of vanish at the same time. But another strategy could be to go just really, really far from that critical regime, right? If you go far from that zone of complication, then maybe you can get rid of that. And this is what we'd like to do, right? If we could only prepare glasses that are really, really far, really well beyond the dynamical transition, then maybe we would be in a better situation to test the beautiful parts of the paradigm shift. And there's a try, tested, and true method of doing this, which is to take simulations and to let them run, and to wait, and to wait, and to wait some more, right? And then at some point, the PhD clock is ticking, so you start making measurements. And actually, the experimentists are a bit luckier or smarter, or a mix of both in this context, right? They said, well, maybe as a PhD student, I can't wait for, I don't have that much time over my thesis, but I could look for geological glass, right? If I can only find samples that have been aged for all this time, have been prepared, then I can study those, and then I have my prepared glasses at the time. And actually, at the time, 10 years ago, this was roughly the best way of obtaining those ultra-stable samples. And in the simulation world, if only Metropolis had started glass simulations of hard spheres in 3D straight in 1952, maybe we'd be in a different simulation, but didn't have that wherewithal. And actually, if you do back of the envelope calculation, just to speed up with which the computers have gained, it wouldn't have changed anything, right? So we're sort of stuck in that respect. Now, experimentalists have come up with a really smart way of looking at this, and Mathieu mentioned it during his talk, was to try to vapor deposit glasses layer by layer slowly. And it turns out this way they obtain glasses that are ultra stable. But one of the advantages of simulation is that we're not bound by rules of standard physical dynamics, right? This is where the idea of swapping particles from the 2 different parts of the system come from, right? And as Mathieu said, this is really not a new idea. right? This has been around for at least the 80s. Practitioners in the field, Don Frankel thinks it actually was probably used in the 70s as well, and people, actually it was so obvious as a trick to sample phase space that Don's hypothesis, or one of his hypotheses, that maybe people didn't even mention it in the papers because this was so obvious, right? So it's an old, time-tested way of sampling configurations. What was really, and it works only to some degree, right? If you choose your favorite model, you try to swap. Sometimes it works, sometimes it doesn't. Depends on the particular details of it. And what was really, really smart, and the real insight that Ludovic Berthier had 2.5 years ago, he said, well, why don't we reverse the question, right? Instead of trying to look for the best algorithm to optimize my glass former, why not just look for the best possible glass former for the algorithms I do have, right? And if you flip around this question, this is where you come up with the swap, right? The swap approach. It turns out you can do pretty marvelous things in terms of dynamics, right? And obviously you can't really measure those speed up directly, but it's estimated that the speed up you get in 3D from optimizing the size distribution of particles is about 10 to the 10. That's a lot of PhDs, durations, right? If you do the same thing in 2D, it's more like 10 to the 42. That's a few lifetimes of the universe. Actually, many, many of them. Right? And if you want to know what happens in higher D, there's the poster that actually Giorgio prepared is still up. Right? And this is what those simulations would look like. Right? So they don't, then the particles are coded by sizes, so they don't all, as you can see, the colors themselves changes, so there's both a translational part to this dynamics and there's an exchange part of this dynamics. And you can see, actually, if you were to stop exchanging, this would look completely stiff. There would be no obvious structural relaxation. And as soon as you turn the swap, it fluidizes. Great. Now, once you,
So this diagram we showed before, it's for identical particle, right?
It's for a
identical sphere, more specific. But this swap operation works for polydispersity. So that I'm a bit confused.
because you think that the universality class is super fragile, and as soon as I introduce some polydispersity, everything must change dramatically? Or, I mean, the experimentalists have been doing colloidal suspensions of polydispersed particle for 20 years, and we never really questioned them on that. So, I mean, and we can actually show, and I should be fair, Francesco was actually looked at by dispersed systems already in 2009, and as long as the system does not fractionate, so if you have a well-mixed system and that does not crystallize, the rest is playing with the commas, playing with where the decimal points are. Right? That's okay. Now, if you do this, it actually opens up, well, the kind of phase space, of parameter space you can explore. Right? While we used to be stuck in this simulation mess region where everything is complicated and mixed with activation and criticality, you can now equilibrate densely supercooled liquid along this line here. That's the analytical continuation of the low temperature, of the low density, equation of state, quite deep. Right? And you can start looking, if you look close to dynamical transition, this Gardner transition that I'll get to in a moment gets really tight with the dynamical transition. If you move further and further away, you can actually separate them, and you get a very clean regime of, say, of one compression, that will be of one type, and then jamming at very high packing fractions, and some sort of transition maybe in between. Right? So it now becomes within the realm of possibilities. Now, the rest of this talk will be structured to follow. First, I'll talk about the Gardner transition by popular request. And then I'll talk about what can we say maybe about the end of this line from looking at, now that we can reach deeper and deeper along this line than maybe it was possible before, can we say something more about where it ends, if it ends at all? So here's my 2-minute version of understanding the Gardner transition in hard disk system or hard sphere system. This is a cartoon, obviously. So if you think you're starting from what you have is an equilibrated liquid configuration, right, at the start of your compression, and where you end up are jammed configurations at infinite pressure, right? And if you start from this region, if you look at, let's say, the maximal number of kissing spheres you would have, the sort of bound on that number grows exponentially with dimension. So you have a lot of neighbors, something like 6 in 2D, 12 in 3D, 24 in 4D, 48 in 5, etc. Right? It grows reasonably quickly, and these are the people that immediately surround you and form your solvation shell in chemist parlance. But if you go all the way to jamming, as Mathieu said, the particles that are actually in contact with you, that are actually making a mechanically touching one another, is 2 times the dimension for a marginally stable solid. Right? So somewhere along the way, you had to go from a vast number of neighbors that seemed, for all intended purposes, equivalent, to a very small subset of those, at least in the high dimensional limit, that are your nearest neighbors. And one way to think about this is that for a while, maybe you're capable of isotropically compressing your glass, but at some point, you need to start making decision. Right? You can't be friends with everyone at the same time. At least you can't kiss them all at the same time. Right? So you have to choose whether you're going to be closer to one set of your neighbors or another set of your neighbors. And the decision that one particle is making cascades on to what other choices those 2 particles can make, and et cetera, and et cetera, et cetera. Right? So you can think, if you think about, let's say, a phase space representation of what this would correspond to, so you would have to, so we have a constrained region of phase space, which is your glass, where particles can move and oscillate, and then as you compress it, it breaks down into subclusters of subclusters and subclusters. And at least the theoretical predictions is this would go all the way to jamming, and this would have a full RSB character in structure. In the infinite dimensional limit, this is what it would have to be. Right? So now that we had liquid structures really well equilibrated, where we can get rid of the marginality associated with the threshold and the complexity associated with that line and the dynamical transition, we can examine a compression. So this is an example of what you could be looking for at a Gardner transition. So this is the mean square displacement as a function of time for a glass configuration, right, to begin with. It's a very, very nice plateau. There's no remnant diffusion. It's really ultra stable in that sense. And if you keep on compressing it, the cage shrinks and you just see a very nice plateau. And at some point, aging seems to be kicking in. Right? And there's more and more aging as you go to higher packing fractions. At some point, at some point this will be really fully caged. And you can compare actually this plateau height with what you would get from taking 2 copies of the system and compressing them independently. And if you compare the overlap between one another, the 2 copy will explore the entire basin, say, and the single copy will have a mean square displacement that gets more and more hindered. And you can compare those 2, and this is a function of the initial liquid packing fraction, and you see that the 2 start to separate at some point. And at least if it's a transition, it's not clear it's a transition. I'll get back to this in a moment. But if it's a transition, it seems to grow sharper and sharper, more visible as you increase the density of the liquid you started with, right? You can imagine that this is due to the fact that the marginality associated with threshold is less and less interfering with that relaxation, so it becomes easier to do so. Now, the argument I just made, I could translate in a different family of system. Right? I could think of having, say, a crystal, right? A crystal of hard disks that I compress uniformly, and if they're all exactly monodispersed, as I compress them, they'll all become in exact contact at the same time. Right? This is what would happen, well, not in 2D, it turns out, but if you do the 3D version of this cartoon, this is what you would get. But if you make your crystal of particles slightly polydispersed, and you don't allow swap in this case, right? You're sort of freezing in that disorder. As long as the spacing between the particles is larger than the typical polydispersity, measure polydispersity, you can isotropically compress that crystal. And at some point, you need to make decisions. You need to decide whether the large particle is going to be next to one set of neighbors, forming contacts on one way or the other way, and then, again, this trickles down. Right? So you can imagine that this phenomenology would have an equivalent maybe in polydispersed crystal. And if you look at hints of a Gardner-like, I should say, transition in this context, or you actually measure the same observables and you see the separation of the 2 quantities. And actually, if you go all the way to jamming, you can extract critical exponents that are associated with or in a similar or related to the SK critical exponents and so you get something that describes the weak forces, something that describes the weak, the small gaps between particles. In the case of amorphous solids, the black lines here, which are the theoretical predictions, actually coincide really well numerically. This is the success of the discussion between Mathieu or the interface between Mathieu and us over those years. What's interesting in the system where you do have some sort of long-range correlations in the structure, right? They're not amorphous. They're, to some degree, those exponents start to deviate from those values, and actually they seem to violate a bound that would be based on an assumption of homogeneity in terms of the disorder. So there's maybe even some new physics there. And I should say, this is a paper that it's not published for one thing, but it got really heavy input from all those other letters that are not authors, but are very instrumental in making this happen. Now, anyone who thinks about the Gardner transition might make some analogy in a field theory sense, make some analogy with the Almeida-Thouless transition, right? It's been mentioned before, and it's well known that this is a spin glass in the field. This is related to Martin Mayer's talk this morning. It's well known that in the perturbative sense, right, there's no fixed point below the upper critical dimension, which is 6 in this case. And so this calculation was done already in the 80s. And for a long time, that's a source of the debate, right? In a sense, that's one of the contributions to the discussions between the droplet model and the full RSB description, at least. Anyways, there's a bit more to this. But what's interesting is that there's a proposal that came out or was motivated by the fact that we were seeing something that looked like a Gardner transition, even though if it were in the same universality class as the AT transition and that transition should not exist, well, the Gardner transition should not exist. Well, so what we did is, what actually you should say Show did to a large extent was a 2-loop computation. And you see in that case is that there's a non-perturbative fixed point that reemerges. It's not a proof of existence in any way, right? It's a non-perturbative result from a perturbative calculation, but it does suggest that there's a possible other scenario, and Giulio and Pierfrancesco and others have actually looked or thought about this proposal as well from different viewpoints. So that's one possible resolution of this, though the jury on this particular question is still out. Now, getting back to point number 2, which was the actual end of the liquid equation of state, right? Whether or not there exists a Kauzmann transition, which would be sort of validation of the RFOT scenario, if not for the dynamics, at least for the thermodynamics in that regime. So having access to those really dense liquids, or the very deeply supercooled liquid, we can enables us to make measurements that used to be controversial, right? That used to be full of assumptions, and we can remove a lot of those assumptions. And this is what we did, with the group in Montpellier last year. Actually, look at different measures of what's called the configurational entropy, right? And see if they all more or less agree, right? And it turns out if you measure V of Q, now I use the standard notation. And tilt it by a certain amount to be able to determine the extent to which you need to bias to. So there's a measure of the configurational entropy. You can also measure directly V of Q. You can look at the point to set correlation, which is this correlation length that Giulio and Jean-Philippe proposed a while back, and we could measure in the system again, make it grow more than it's ever been, in part because we have access to those deeply supercooled configurations. And use, in this particular case, this one is maybe the more naive, the one that's more full of assumptions, right? And is sort of an upper bound for what the configurational entropy should be, which is assuming that you have a harmonic solid and including the harmonic vibrations, or sort of Franke-Ladd integration. They all seem to point to the existence of a finite density in this case, finite pressure transition. Right? It's not super convincing because we do go beyond what's been measured experimentally before, We go well beyond what's been measured in simulation before, but it remains an extrapolation, right? But it's just less of an approximation, less of an act of faith than it ever was. And this is what we see in 3D. The interesting new result in this respect is that we can repeat, now that we know we can go something like 10 to the 42 faster in 2D, can we do any better? Right? And now we can actually measure also the point of set. So the growth of the correlations is what you see here. These are different sets of measurements, but that you can rescale by, there's an arbitrary factor. And now we can go well beyond what would be, any reasonable experimental timescales. And what's interesting in this case is that it seems that if you extrapolate to zero configurational entropy, where the Kauzmann transition would be, this would correspond to a 0 temperature case, or in the case of hard interactions, to an infinite pressure case. So while in 3D, there's a lot of things that do change, and there's a lot of things a lot of caveats in taking the infinite dimensional picture and transposing it in 3D. We do get qualitatively maybe a same scenario of RFOT, at least from the thermodynamics. In 2D, there's something that seems generally different. It seems that you should be able to go straight from the liquid to a jammed configuration at a fixed density, if that's true, or that you do have a Kauzmann transition, but it's at 0 temperature, so it doesn't seem to be below the upper critical dimension for that. So this is where we are now. The work is not over. There's a lot of questions that remain open that I've brushed over. One thing that's especially remarkable is that the jamming exponents, the universality class that was discussed in Pierre-Francesco's context, these exponents seem to be super universal in the sense that they're the same from d equals infinity to 2D. And why that is remains a subject of debate and questions. What about two-level systems? Maybe they're due to ultrastability. This is something that's still being. What about quantum fluctuations? Do they play any role? The Gardner transition might not be a Gardner transition. It might be a crossover. There's definitely a lot of numerical work that needs to be done in this respect. But it's also quite remarkable how strong of a low-dimensional trace it does leave, right? So it might still be relevant in one form or another, even though, at least in some family of systems, even though it might not formally exist in the infinite dimensional, in the thermodynamic limit. The role of length scale fluctuations, of small length scale fluctuations, local critical dimensions. What is the finite D echo of the dynamical transition? As you saw from Mathieu's talk, this is, up until a few years ago, we thought we understood this. This was an old topic, and it's been completely brushed anew by the advance of the swap results with a discussion that Mathieu and others are having. And then the question, obviously, throughout all this is what's the role of activated processes? Giulio is pushing in this direction. There's a lot to be done. It's a very difficult problem, but we're, I think, on the best track we've ever been to taking it home. So with this, I'd like to thank you for your attention.
Thank you. Thank you, Patrick. We have time for a few questions, if any. Are there questions? Or remarks? Everybody is happy?
Or hungry?
Can I ask a stupid question?
Please do.
Coming from a completely different field. I come from fluid mechanics. There are a lot of situations where when you move from 3D to 2D, the system completely changed behavior, right? And what we have learned that is also very important to study what happens in between. So studying, systems where you can slightly squeeze the volume and going smoothly with a control parameter from 3D to 2D. Is something doable also in your cases, or as soon as you have more than one layer, everything is 3D? It's because you see such a big change between 3D and 2D that is.
As you saw, there's in Martin Mayer's work, right? They're trying to interpolate between 2D and 3D by thickening samples systematically, by controlling the perpendicular length this way. There's been some numerical work in spin glasses in between the two. The work in hard spheres in partial dimensions is a harder.
Or even
abstract problem.
In squeezed volumes.
In squeezed volume, Actually, in squeezed volume, you are immediately in the lower dimension, right? To some degree, right? So if you people have looked at systems in cylinders, which are obviously quasi one-dimensional, and it has a universality class of
it's
one-dimensional
completely critical, singular.
Yeah. Looking at thickness, it turns out that systems that have been deposited to a large extent. So actually, I should say maybe that one of the interesting new insights that come out of studying the vapor deposition process is that it seems that the surface, or it's been postulated, and it seems to be true that the surface controls the relaxation of the glass as you deposit it, and this very fast 2D dynamics with potentially non-local moves, if it were not confined, it might be at play in relaxing the system this way. So that's one way in which it's been studied. The studies in confinement have been done to some degree in the 90s and 2000s. They've not been redone. Obviously, with new equilibration algorithm, there's many new possibilities. But yeah, that's the best I know for now.
Are there other comments or questions? If not, we can thank Patrick again. Thank you. We have now Jean-Philippe Bouchot.